Hello, and welcome to this dynamic section of the ICM 2022 on the 9th of July. My name is Anish Ghosh, and I'm a mathematician who works at the Tata Institute in Mumbai, India. I'm very pleased to welcome all of you to an excellent session. So to kick things off, we will have a talk by Professor Miklós Abert from the Reni Institute in Hungary. His talk is titled Groups, Manifolds, and Graphlins. So Professor Abert is an expert in dynamics and also an expert in group theory and the interactions between group theory and dynamics. Now, one thing about this talk is that it's a pre-recorded talk. And so we will not, unfortunately, be able to take any questions. So Miklós has asked me to tell all of you that he welcomes questions which can be emailed to him at his email address, which can be found on his web page. So without further ado, we will now start the talk by Miklós.
So it's always nice to be here, especially in Israel, especially in Jerusalem. And so this is also my ICM talk, so it will be recorded and then broadcasted. But I don't care much about that, frankly. I honestly don't care much about the virtual format. So I care much more about having a mathematical dialogue. So let's do it in the Israeli style, okay? So just interrupt me whenever you have something to say that is related to the talk, okay? So and the rest tell me after the talk. So. Actually, you know, I learned a lot from Israeli mathematics. As a PhD student, my role model was Alex Lubotsky, as I guess for many of you. And then, I was thinking about what is the biggest thing I learned. That it's exactly this style of seminar format, where there is a free discussion going on. So let's keep this up. I mean, if you don't interrupt me, I will get bored, and then I promise you that you will get bored. So. Yeah. Also, if I'm too fast or if something is not clear. Okay. So I want to tell you a story today, and I don't know whether I will finish the story. It's also less important for me than having a discussion. So it's about a curious problem that I started to care about when I was a PhD student, and I still care about it. And as I was thinking about it over the decades, it led me to a lot of, off-strays. And a lot of directions in mathematics and results and counterexamples. So I try to put everything on this tree, which will do some injustice to the math. So since I will say the story from this perspective, you know, I won't be able to tell this very round talk. The same with giving credit. So I won't give all the credit where I have to give the credit. You can read my ICM paper if you want, and if you want a properly recorded online talk, then go to YouTube and search me on YouTube, and you can find free talks, and one of them is actually not bad. So the one on invariant random subgroups. So if you like that style, then be my guest, and you will increase the number of watchers by one. So I will know. So okay. So the object we are looking at is a group theoretical invariant called the rank, or minimal number of generators. So gamma is a group. It's a countable group. And d gamma is the minimal number of generators. Can you see what I'm writing? Is it visible? Yeah, cool. Okay, it's also called the rank, and I will call it the rank, although that's, of course, an abuse of that poor word, because it's used for at least 20 things in mathematics, okay? Since the rank of a group is the minimal number of generators in this talk, okay? So you can just study the rank, I mean, give estimates of rank, but it's a very mysterious invariant. You can give estimates, lower and upper estimates, but it's really not easy to find the exact value, even for interesting groups. So also you run into surprises. So there are certain groups, like the symmetric groups, on rank n, you know, a natural generating set has n choose 2, size n choose 2, you know, all the transpositions. Another one is just the neighboring transpositions. That's a minus 1. But it can also be generated by 2 elements. So what I'm saying is that it's an algebraic invariant or a homotopical invariant, which makes it hard to compute it. Anyways, we were really interested in that invariant. And so what you can do when you have such a mysterious invariant, you can look at it, you can normalize it or try to tame it, look at its growth over sequences. So that's what we will do. So if H is a subgroup of gamma, of finite index now, okay, then of course, you know, you all know the Nielsen-Shire theorem for free groups, for the rank, how the rank behaves under taking a finite index subgroup. So we will introduce this thing called R gamma H, which is just that, it's just D of H minus 1 over the index gamma index H, okay? And then this is always less than or equal than D of gamma minus 1, simply because when gamma is a free group, then there is an equality, which means that when it's not a free group, then there is at least an inequality, okay? So this is trivial, and it's also an easy exercise that when you have two subgroups that contain, that one contains the other, okay? So exercise, if gamma H is a subgroup of gamma, it's a subgroup of K, then R gamma K is less than or equal than R gamma H, okay? So in particular, when you take a descending chain of finite index subgroups, so for gamma equals H0, H1, etc., all of them are finite index, you know, the rank gradient of gamma with respect to Hn, which is the limit of these guys, of R gamma Hn exists, because it's a monotonely decreasing sequence. So again, this R is nothing. It's just the rank minus 1 normalized by the index, okay? You have to put minus 1 there because when gamma is a free group, then this is a constant sequence. So it's nicer to keep it that way. So only for that purpose, I put that minus 1 there. Does this make sense? Okay, so that seems like something you could do more damage to than the original rank notion, because it's a normalized limit of this mysterious invariant. And it turned out that this is still not so easy to understand. So perhaps the first question that one would ask, okay, so you get an invariant for this chain of subgroups. Does the limit, the rank gradient, depend on the chain? Okay, this notion is due to Leck-Canby. So does the rank gradient depend on the chain? Now, normally, I would have you solve this exercise, but not now. So yes, it can depend for very stupid reasons, like you can take constant sequences. Now, you all hate that, right? But you can take the product of two free groups, F1, well, whichever, F2, okay? The direct product of two free groups. And then if you walk down on a chain that only sees the left-hand side, okay, then the rank growth will be positive. Okay, because of Nielsen-Shire. This guy has constant rank. You walk on this side, so the growth of rank will stay positive. But if you walk on a normal chain that bites into both sides, like the normal chain with trivial intersection, then the growth of rank will be 0. So it seems like that's the end of the story. Of course, it depends on the chain. It can depend on the chain, but that's That's still not convincing, and part of the talk is to convince you that this is not convincing. It's a convinced, non-convinced issue. So what is still an open problem, and we don't know? So open. So let Hn be normal in gamma, a chain, and Kn be also normal in gamma, both chains. Does it follow that the rank gradient of gamma with respect to 1 is equal to the rank gradient of gamma with respect to the other? So assuming that both chains are normal and they have trivial intersection, I didn't say that, and the intersection of Hi equals the intersection of Ki equals 1, okay? So they kind of both approximate the group by finite quotient, okay? Can the rank gradient still be different, okay? So we still don't know any example for that, strangely. We can prove this in many cases that it does not depend for certain groups, but we don't know a counterexample. Okay, so what's going on? So what do you do when you hit this problem? This whole investigation I started with Nick Nikolov. So we started to think about it by ourselves. We didn't even know at that point that Leckamby defined this notion. And so what do you do when you have such a problem? I mean, you can prove vanishing results. And that's, so let me see. So A, what do you do when you run into such a problem? So prove vanishing results. So say that for certain groups, for any normal chain, the rank gradient is 0. Okay? Then once this is true, it's independent of the chain. Okay, the second thing you can do when you're in pain is that you can ask for related invariants. Related invariants. So, okay, let me ask you, which invariant would you relate? Just the rank. If you had to estimate the rank, I give you a group, and I give you a million shekels if you can estimate the rank well. That's not going to happen, don't get your hopes up. But, what would you try to compute? No, honestly. What would you do? Yeah, I mean, what else would you do, right? So you would take the first homology. So the rank of the abelianization, that's always a lower bound. And you would hope that it gets close to that. So we will talk about this and other invariants that are neighbors of this. Okay, see that you can try. So express it differently in other languages. And by that I don't mean that you should translate the notion to French, but you should translate the notion to ergodic theory or something. So, which is something we will do. So, okay, and D, and that's my favorite kind of exercise. When everything fails, try to understand what the heck you're really asking. So look around. Look around honestly. I mean, try to understand where this whole stuff comes from. What is the meaning of what you want to prove? Because, sometimes there is a meaning of what you want to prove, and then sometimes it even helps to know what it is, even in modern research mathematics. So, okay, so that's the story, and I want to tell you what kind of things we did here. So for the vanishing result, first I just write an easy exercise that any one of you could do if the center of gamma contains an infinite order element, then it vanishes. Then the rank gradient is 0. if you care to, if you're the type of person who likes to do exercises, that's your way of understanding, this is a good exercise to get into this thing. So then later we will see that you have much wider vanishing results, but let's stick to this. So related invariants, so first, Betti number, which is just the dimension of the first homology over the field, over the rational field, okay? Or if you want to go wide, you can do mod P homology, which is a much more mysterious thing, so it's much harder to understand, but you can do it. That's still lower bound for the rank. So the mod P abelianization instead of the abelianization, the free abelianization. And then we will put more things here, but not now. So express it in another language, and this is where the real fun started. So I will talk about that a bit later. This is like a promise. It doesn't look like a promise. Okay, I promise I will do it. So, and the last thing is, so let me just write the calling word. It is cost theory and fixed price. You know, this notion of fixed price, it's getting into fashion nowadays, right? It's like it starts to be an important notion. And the last one, you know, look around honestly. What does it mean? Here comes Benjamin-Ishram convergence. V containment. Let me put a warning here. This will be a failure story. This will be a story of how we try to do something which fails, but it fails in an interesting way, so I want to tell it. V containment and IRS. If you're American, don't get scared. It's not the authority. So, okay. So where should I start? So maybe I should start the story not by the vanishing results. Let's do it here. Okay, express it on another language like cost and fixed price, because that's the one I will only briefly talk about, because that would take a whole lecture in itself. So let X be a standard Borel place, standard Borel space, not a Borel place. With a probability measure, and let gamma act on X mu by P and P max. Okay, then this action has a so-called cost. So cost of this action. And unfortunately, I won't have time to define it. It's a number. So it's a number between 1. So the cost is a number between D and 1. And this notion has been introduced by Levitt, but most of the deep work on it has been done by Gaborio.
So which was D is D of gamma?
Say it again?
D is D of gamma?
Yeah, the number of genders.
Yeah, D is D. Oh, yes, that's right. D of gamma. Thanks. Exactly. Yeah. So
Is cost an integer or is it?
no, cost is a real number. And it's actually, it's some kind of minimal number of generators, okay? But I say this sentence, but I won't be able to explain it. I won't have time to explain it. So if you look at this, if you look at the measured groupoid coming from this action, let's assume that the action is free, okay? And look at the measured groupoid coming from this action, then this is, and then you take a generating subset for the groupoid. So you take a Borel subset for the groupoid that generates the groupoid as a groupoid. This is the infimum measure of a generating subset, Borel subset for the groupoid. I won't even write it to the board because I won't have time to explain. So it's a very nice theory. it's the measured theory of rank, if you want. So Gaborio did a lot of nice things with it. For example, he did the favor, one of the theorems is that if gamma is amenable, then every free action of gamma has cost 1. So it takes the minimal value, okay? It's somehow minimally generated, okay? He proved many other beautiful theorems, and look up the literature, it's beautiful stuff. So, okay, fine. So how do you relate the two? This is my first theorem with Nick. So what we proved is that when you have a chain of subgroups, so you can take the tree of cosets for a chain of subgroups. So you can take the cosets gamma modulo gamma n, those the coset spaces. This forms a rooted tree by setwise inclusion, okay? And gamma acts on it. The coset actions respect inclusion, so this gives you an action by automorphisms on this rooted tree, on the coset tree. Does this make sense? Are you happy? That's two different questions, but nevertheless. Okay. So, yeah. So now, this is still a countable set, and you have an action on it which is transitive on every level, right? But now you go to the boundary of the tree, okay? And you put the product measure there, the natural measure there, just the random choice measure. And then this action, of course, extends to the boundary. So you get a PMP action. This is called the coset tree boundary action. So this is delta t of gamma with respect to Hn. Does it make sense? So the theorem is that the rank gradient of gamma with respect to Hn equals the cost of this delta t action minus 1, okay, assuming the delta t action is essentially free. It's free. So free just means that a random point here has trivial stabilizer. Okay? So that's great. Once you have this theorem, you can translate a lot of the stuff that Damian and friends did and get new theorems of rank gradient. For example, it follows that amenable groups, if gamma is amenable, then the rank gradient vanishes for any normal chain with trivial intersection. Actually, later we proved this by hand using like honest group theory, like elementary group theory, but it was using one of Benji's early papers. But it's not trivial, so you gain energy by this translation. Okay, so fine. So that's a relation. Now, of course, then there was the two communities kind of started to talk and meet, and there was a lot of good interaction and joint work with Damian and his group. So it was very nice to find this connection. The other connection that is very, very important, and you all have to know about it, this is the related invariant, the first Betti number business. So you can try to do the same. Instead of rank, just take the growth of the first Betti number over chains of subgroups. Okay? So it turns out that the answer is yes. You know, the growth of the first Betti number is independent of the chain, and everything is beautiful. Sababa. So, theorem, this is Lux theorem. And I'm not saying it in complete generality because that involves higher Betti numbers, but don't worry about it. Look it up. So if gamma is finitely presented, and gamma n is a normal chain in gamma with trivial intersection, sorry, I called it H before, so intersection Hn is 1, then the limit of the first zero characteristic Betti number of Hn divided by gamma index Hn equals a number, the first L2 Betty number of gamma. So you get something that comes from L2 cohomology, which uses, the definition is like cohomology, but it uses von Neumann dimension and L2 chains. And I won't have time to define it. So it's a number. The important thing here is that this guy doesn't involve the subgroup. It's an invariant for the group. Hence, the growth of Betty numbers is independent of the chain. Okay? So an open problem, which is a very annoying open problem for me, can it happen that these two guys differ? Okay? So can, the rank gradient of gamma with respect to gamma n be not equal to the first L2 Betty number, this limit. Okay, this is still open. So if you think about it as an honest, elementary group theorist, this is crazy to ask. I mean, this tells you that for any finitely presented group, I'm not telling you why finitely presented is needed. There is a reason, just believe it. For any finitely presented group and any normal chain, the asymptotic growth of the first Betty number is the same as the rank. So the asymptote, this stupid abelianization would control the homotopy complexity. That would be if this would be true, and we don't know any counterexample. Okay? This sounds very, very hard to believe if you're looking at it from this side, but we never found a counterexample. So then you can ask the same question. Of course, you can instead of Q homology, you can ask it for mod P homology. Oh yes, absolutely. So this is always less than or equal than the rank gradient. Simply because individually the rank upper bounds the individual Betty number. Yeah, I can write -1 here if you want, but it's a limit, so it doesn't matter. Yes.
Subgroups where you have equality, or that's not?
Say it again.
Can you find special subgroups where the answer is if you have equality, or not?
Yeah, for a lot. Well, okay. So first of all, the cheap answer is once you have vanishing of rank gradient, there is no room to move for the other guy. So. I don't know, I cannot tell you anything sexy, so about this at least. So, yeah.
Do you have a group for which you conjecture you have the equality?
No. But I also have to warn you that the reason may be that finally presented groups with positive first L2 Betty number, where it doesn't vanish, are fairly rare. So it could be that at the end of the day it will be some characterization which I would hate. But it's true, but not for the right reason. It's true because there are no counterexamples. Since I left finite group theory because I couldn't cope with using the classification but never understanding it, this would be the worst solution for me personally. But of course, math is not out there to make me enjoy. So who knows? But okay. So does this make sense? So you can put there is a natural invariant between the two, the Q homology and the rank. This is the mod P homology. But for mod P homology, we don't even know that this growth exists. So it's still open. Open does if you take does B1 modulo P for a fixed P, Hn over gamma index Hn, does the limit exist at all? The reason why this limit exists, the Lux approximation theorem, is honestly spectral theory. So you translate the whole thing into spectral theory, and you prove a strong convergence theorem on the spectral measure, or eigenvalue distribution of certain operators. And that's beautiful and fine, but this spectral theory is completely missing mod P. Mod P, we don't know how to associate any analytic object that would tell us. Gaborio and Brandon Suat has a nice paper about this, but it doesn't solve this problem. So, okay. So, all right. So, in particular, what I did not tell you and I should have told you about this cost theory is that another open problem, this will be the day of open problems, it seems. So this no one knows a group and two free PMP actions with different cost. So is cost a group invariant? This is the fixed price problem of Gaborio, and it's still open. This is kind of the big brother of our original question whether the rank gradient can depend on the chain. In particular, if you refute that question, if you find two chains with where the rank gradient is different, this solves this problem, Gaborio's problem. It gives you two PMP actions with different costs. All right. So before I go further, let me talk about, of course I won't have time to cover the whole thing. So one of the nice things that I was thinking a lot about this problem over the years. I'm not saying that I was thinking with the same intensity. You know how it is. I mean, it's like most of the time when you say that you think about a problem, all you do is jump back and forth into bushes, sometimes the same bush, and you do kind of exercises, but like in the army or something. But I was thinking a lot about this question. So some things so this was the original problem that got me into graph convergence. So Benjamin-Isham convergence. And also later into the notion of invariant random subgroups, but that story I won't be able to tell. If you really want that story, just watch the YouTube video. Watch any YouTube video or watch my YouTube video. I can tell you the Benjamin-Isham convergence part. So when you have such a hard problem, you want to know how could you refute it? I mean, what are you missing? So the first thing that you're missing is that why take normal chains? Why not take chains of subgroups? Why do you need normal? Why do you insist that the intersection is trivial? What's the exact thing? Because if this would, saying that a normal chain with trivial intersection approximates the group is a very bad limiting notion, because I can take two normal chains with trivial intersections and I cannot merge them. If I merge them, it's not a normal chain with trivial intersections, so it's a priori not a good convergence notion. So we were kind of wanting to understand what is the good convergence notion. Is there a good convergence notion of subgroups which tells you that these subgroups approximate the group? Okay, and actually there is. And which one should I erase? I think I will use this one. So this notion, as far as I know, first appears in a paper of Farber, where he generalized Lux Theorem on Q homologic graph to non-normal chains. So still chains, but not normal chains necessarily. So it turns out that the following, where did I write this? It's here, okay. So this is not Farber's theorem, this is our theorem. It's not even a theorem, it's a proposition, frankly. So gamma is generated by finite symmetric set S, as usual. Gamma n is a chain in gamma, finite index chain, then the following are equivalent. Okay? So for every element other than G, in gamma, if you take the fixed points ratio, so the fixed point set of G acting on gamma mod gamma n, normalized by gamma index gamma n, it equals 0. This was Farber's condition. The second is that the invariant random subgroup defined by gamma n as an IRS weakly converges to the trivial IRS. So this is about invariant random subgroups, and it's just weak convergence of invariant random subgroups to the trivial invariant random subgroup. The third thing is that the quotient Schreier graphs, gamma modulo gamma n with respect to S, Benjamin and Schramm converge to the infinite Cayley graph of gamma with respect to S. I will talk a bit about it. I won't talk about IRS here, other than just say a sentence. And the second is that the action gamma on gamma mod gamma n is a Sophic approximation. Okay? So again, IRS would be a different lecture. This is self-containment. And what does this mean? So this means that as you look at the quotient Schreier graphs with respect to S, yes?
When you say chain, it's not necessarily...
No, sorry. It's not even a chain. Yeah. Sequence. Thanks, Benji. That's correct. Yeah, you don't need it anywhere. If it was a chain, then I could add that on the coset tree. The action is free. Yeah. But I want to get rid of chains. That's the point. So, and this kind of chain thing. So, what does this mean? This means that when you look at a deep gamma n, a deep index gamma n, and you look at the random point of the Schreier graph, a uniform random point vertex of the Schreier graph, you won't be able to distinguish it locally from the infinite Cayley graph. When you look at it in some bounded neighborhood, you may think that you're already, the infinite Cayley graph because the balls are these balls are isomorphic. Okay, so in other sense, the injectivity radius tends to infinity in distribution. You're looking at from random points. From most points, the injectivity radius grows. Okay. So the others are equivalent to it. And this kind of equivalence, although it's trivial, if you sit down and understand that the hardest thing about the proof is to understand the definitions. But this is a lot of different languages, and this invoked a lot of interplay between the different fields where it came from. That's why I wrote it to the board, not because of its inherent mathematical hardness. So I only wanted to say one sentence about IRS. So we did coin the name IRS, invariant random subgroup, but we did not invent invariant random subgroups. Invariant random subgroups were present in the Margulis school, and they wouldn't be surprised by the notion at all. The new thing that we added, other than coining the name, is to analyze exactly this. The weak convergence of invariant random subgroups and its connection to Benjamin-Isham convergence. That's the new ingredient that we added. So the notion is not ours, and we never claimed that it was, but I got some grief for this, so it's time to clarify. The other thing that is good to clarify is that some people told me that Benjamin-Isham convergence shouldn't be called Benjamin-Isham convergence. First of all, we are very late to that party, and because everyone calls it. And second, it's true that they did not invent the notion, and they never claimed so. Probably it's due to Aldous, but actually it goes back to Fürstenberg, by the way, Fürstenberg correspondence. It's Fürstenberg correspondence for graphs, actually. And then you can ask where Fürstenberg correspondence goes back. And then I did try to look, and this is these questions are exactly like where the Danube starts. You know what the Danube is? It's a big, where you have a big river, where does it start? That's, there is always a small thing and another small thing meeting, and after a while you call it a river, but where does it start? So I think for Danube there was a big fight about this, because of course every village wanted it for touristic reasons. So we are not that much of a tourist, but I think it's a good practice to bind the name to the first paper, the authors of the first paper, where something super significant was done, so that people really started to care about this notion. So because of that, this is completely rightfully can be called Benjamin-Isham convergence, because That's what raised people's interest in that, hands down. Okay. That was kind of a service announcement for the community or something. So, okay. So there is only one more thing that there are many more things that I would tell, but there is one more thing that I have time to tell, and this is the failed attempt, because it's good to talk about failed attempts, right? So how would you prove that a failed attempt and then maybe a new direction? So I think I will have time for both. So we tried, in desperation to prove that the rank gradient is independent of the chain. And we figured out that there is one thing that you could do. There is this gamma, and then there is this coset system, and there is the other coset system. So gamma modulo gamma n, gamma modulo delta n, right? These are two normal chains with trivial intersection if you want. Okay? Fine. How can you relate the both? Well, locally they look the same, and globally they may look very differently. So how can you relate the rank? So what we realized is that if you can massage, if you take a guy here and a deep other quotient here, and you can find a map which is almost a covering map. So if this deep big Shire graph or Cayley graph now has a map to this fixed Cayley graph, which is an almost covering map. It's a covering map with small error. And this happens all over the space, so these guys all kind of almost factor onto each other. Then this makes the rank gradient to be the same on the chain. So for a while, we were hoping that one can prove this, that if you take a group and you take two normal chains with trivial intersections, then one can almost cover one with the other. So the failure is that the opposite is true. So failure, this is a theorem of mine with Gabor Elek. If gamma n and delta n have property tau, meaning they define exponder sequences, which is the situation that you care about a lot, okay? And in this way, they weakly contain each other. Then they are refinements of each other. It's the same chain, okay? So it's literally the same chain, just you pick some other, you take the union is still a chain. Okay? So it's the exact opposite is true in the interesting situation. That's life. It's a nice theorem which was born out of, I don't know, born the wrong way or something. So anyways, then it turned out that actually there is a notion of V-containment by Kekris, who looks at it, and indeed this notion is his V-containment notion for the limiting actions. And that prompted us to study V-containment in general. And then with Benji we proved the theorem saying that every free PMP action of a countable group gamma weakly contains the IID actions, the non-trivial IID actions. So because Kekris proved that cost is monotonic for V-containment, this implies that the cost is maximal on the IID actions. So the Bernoulli actions, the non-trivial IID actions, have maximal cost. So if you want to prove vanishing of cost, it's enough to prove it on the nicest action, the most natural action from the ergodic point of view. Okay? And that's a nice theorem, and I really like it. It did not for a long time, it did not bring to life a new vanishing result, because for those groups where we know vanishing of cost, total vanishing of cost, we can prove it by hand on any action, and we don't have to use that it's IID. Surprisingly, this theorem was used much more in Sophic entropy theory. In disguise, this is kind of a quasi-randomness theorem, and those guys could use it. It came handy to them that there is this quasi-random recoding of a free PMP action, and they used it. So, but then recently, and that's the last thing I want to, it's really the last thing I want to tell. So I actually don't care. The recording will stop, I guess, and that's fine. So, or maybe you can speed up. Whoever takes care, just speed up the whole thing and squeeze it into 45 minutes. And then they can slow it down, no? On YouTube. So, this is nasty, right? Okay. I'm a dangerous person, so I have these ideas. So do you guys, can you guys give me 5 more minutes? Okay. Fine with me. So thank you very much.
Okay, thank you for joining us for this lovely lecture by Miklós Abert. So as I mentioned, it was a pre-recorded lecture, so we encourage you to email questions to Miklós. His email address is available on his homepage at the Randi Institute. Thank you very much for coming to this session of the dynamic section of the ICM.